All right. Good morning, everyone. And my name is Ling, Zhuo, and I'm with Chevron. My main job is working as an HPC software engineer and putting our seismic applications on HPC systems. And today I'm going to talk about one of our projects that we did last year to move a seismic imaging application into an external cloud. So there are two main differences between my talk and the previous ones in this session. So first, my talk is more application focused instead of on systems and infrastructure. And the second, I don't have any colorful, flashy pictures. So bear with me. I will try to make up by giving you more technical details. And so we all know that in the past several years, there is more and more cloud presence in the oil and gas industry, especially in the enterprise IT domain. And so, but our question was, is cloud mature enough for HPC applications? Can we move an existing HPC seismic application into cloud? Is cloud powerful enough to do these seismic computations now? So that's the main purpose for us to do this project. And of course, to judge whether the project is successful or not, we have to set several success criteria. So the number one is performance speed up. That's for sure, because we are doing HPC, that's what we do. We look at performance. And the second one is we don't want to disrupt the current workflow for the users. So the ideal case is that they don't even need to know where the computations are done. But yeah, so we try to minimize disruption. And since this is a research project, cost is not our top priority. So I would say we don't consider cost for this project, but actually throughout my talk, I will mention several of our decisions that we made. Actually, we made the decisions based on cost, but we didn't do a thorough cost analysis. That's all I want to say. And there is one ultimate question for this project. Actually, it was proposed by our geophysicists. So they are interested to know, with the unlimited computing resources in the cloud, is it possible for us to reduce the seismic migration time to zero or to close to zero? I'll let you know what happened. Of course, the answer is no, but I'll let you know why. And so let's look at our application. And this is a very highly parallelized seismic imaging application that we run regularly in our on-prem HPC cluster. And it is a typical HPC application where we use MPI pthreads in very large scale. And here, actually, this is a picture of the application architecture. So what we have a user GUI where the user can look at the velocity models and make changes to them, and also they can set the seismic parameters. When everything looks fine to the user initiates a seismic migration job and sends it to the master, which is in our HPC cluster. The master then assigns a lot of tasks to the worker nodes in the cluster, and the workers actually work independently on the tasks. So the good thing is the workers don't talk to each other, but they do have to access the same seismic data set. So that's why we need a very high performance storage for this application to provide the aggregate I/O bandwidth. So when the workers are done, they send back their intermediate results to the master, which does the reduction of the results and then sends the final seismic image back to the user. The user looks at the image and makes changes to the velocity models again, and then probably, usually, the user initiates another seismic migration job. So in the typical workflow, we do a lot of, when they use this application, there are multiple seismic migrations initiated. So that's why the geophysicists really want to take advantage of the computing resources in the cloud for this application. And also we, as HPC people, we think this application is an ideal candidate for Cloud 2 because basically it's embarrassing parallel. There's no communication among the worker nodes, and all we do is a kind of MapReduce paradigm. So what we did in this project is not a pure lift and shift, but more like a lift and improve in the cloud. So we basically took the same application architecture and implemented in the cloud, but we did make some decisions along the way based on the application. So first, we keep the user GUI on-prem. So that makes things a lot easier because we don't need to deal with some licensing problems, and also we don't need to worry about the visualization in the cloud. We keep the GUI on-prem, but only move the computation part into the external cloud. And to set up the HPC environment in the cloud, we used Packer images, which contains the application executables and all the libraries the application needs. And then we use bash script to set up the passwordless login for MPI. So in that way, we set up an HPC environment that is very similar to what we have on-prem. So these are just straightforward steps that you can use in any cloud and for any application. And the next two bullets are more application specific. So I mentioned that all the workers need to access the same seismic data set, and that's why we use Lustre on-prem. So in the cloud, we could, actually at first, we used something similar to Lustre, but it was very costly. So we ended up using another scheme provided by the cloud provider. And it's a block level device which can be mounted by a large number of virtual machine instances. And all the instances have have access to the same copy of the data. So actually that worked very well for our application because in our application, all the workers actually only read the seismic data and not write into it. So this is a one application specific decision. And also we did something very differently in the cloud for the resource management. We didn't use PBS in the cloud because I just don't see see PBS as necessary in the cloud because we just don't need to manage the resource. We just request the worker nodes as needed. So what do I mean here? It's like, actually this is the architecture in the public cloud. And we have a virtual network where the master and the workers are. And the workers, each worker has an access to the same copy of the seismic data. And when the user initiates a seismic migration job, it sends it to the master. And the master uses the cloud CLI to request nodes dynamically from the cloud. And then it sends a task to the workers. And when the migration is done, and the results are sent back to the master just decommissions those nodes. In that way, we don't need a fixed cluster setting up in the cloud that actually is more cost effective. So here is some of our performance results. So we were able to provision up to 900 nodes in the cloud with 16 cores on each node. And the data set we used for testing has 3 terabytes of seismic data and 70 gigabytes of velocity models. And these velocity models, as I said, need to be broadcast to all the workers. And if you look at the graph here, there's a breakdown of our total runtime. So the blue part, it is divided into 3 parts. And the blue part shows the time it takes to broadcast the velocity models to all the worker nodes. And you can see that actually it increases linearly with the number of nodes. The orange part is the part we care most about. It's the seismic migration time. So at first it goes well. When the number of nodes increases, the migration time decreases as we expected. But then when the nodes keeps increasing past 512, unfortunately, the seismic migration time started to increase. So unfortunately, we got a performance regression here. And I'll talk about possible reasons later, very soon. And the green box are just the reduction time for the final result. It's the same as the number of nodes increases. So what have we learned? Did we get the performance speed up we wanted? I would say yes, actually. Compared to a typical run on Prime with 128 nodes and 24 cores each, we actually, if we just look at the seismic migration time, we got a 2 times speed up. That's very good. But if we count the total runtime, including the broadcast time and reduction time, we only got a performance speed up of 10%. So yeah, again, unfortunately, the answer to the ultimate question is no. At least for now, we can't reduce the migration time to 0. So why is that? So we have identified 2 performance bottlenecks that we didn't know exist in our application. Only because when we were running the application on Prime, we didn't have that many of nodes to run together. But when we tried the application in the cloud, we were able to identify these new bottlenecks. So the first, as I said, was the broadcasting of the velocity models. I'd like to abstract it to a higher level, saying it's actually the sending large size of data to a large number of nodes simultaneously actually is the problem. And there are multiple ways to solve this problem. Maybe we can look at different types of MPI implementation, or maybe we just don't use MPI for this at all. Instead, we can use disk or other solutions. And another bottleneck is actually the master, the node which is in charge of assigning tasks to the workers. So obviously, it seems that the master, when there were 900 nodes, 900 workers working at the same time, the master was overwhelmed. Because when the application was written, the master was single-threaded. We never thought of parallelize it, but because we didn't even have that large number of workers on Prime. But if we want to increase the number of workers, definitely we need to work something. We need to change something in the master. So what have we learned? The lessons learned are you can do HPC in cloud now, actually. It is feasible if you know your application well. You have to know the communication patterns, your I/O requirements, and what computing resources you need for your tasks to make different decisions in your cloud options, like what instances you need, what storage option, and what network settings you need to set. And still, even after you do all that, the performance speed up can be very limited because your application was written for a different HPC environment. So if we move up to the cloud, we have to rethink the architecture of the application and change some of our assumptions. So basically, this is just what I said. So for our application, the next step is to revisit our application architecture and see what design assumptions we need to change. And cost analysis is very important if we want to do more work in the cloud. We want to make sure that the user, all these usage of moving to cloud thing is transparent to the user, and they don't need to be, their work shouldn't be disrupted by that. And I believe that all these things can be applied to other applications and also other cloud platforms. And this is for our application, but I think there are something larger and actually larger that we need to do as an HPC community that we need to do. So with HPC in cloud, the entire HPC software development process may need to be reconsidered, and everyone here, I think, including the vendors, the cloud providers, and the users need to work together to find out more solutions. So do we need new programming models? Do we still use MPI, or do we use something like MapReduce? What are the new cloud-native technologies we should look at? Or maybe we should not look at cloud-native technologies if we want to keep running our applications on-prem and also on multiple cloud providers. So these are all questions that I just want to throw out there for the community and for us to work together. And with that, I think that's the end of my talk. I have